In the last session, we saw that cyclic codes are one of the class of linear codes, linear block codes. And also we saw the mathematical formulation behind cyclic codes, and there's a ease with which we can handle these cyclic codes. That is one of the major advantages going ahead in this error control coding. Okay, fine. Then we'll try to extend this theory further to understand more about cyclic codes. In fact, in the last session we tried to encode for a particular given generator polynomial, and the way that we handled was in a very non-systematic way. Okay, although we could able to draw the code table for specific data that is given to us. However, we can change the procedure, or we can encode the data bits in a more systematic way. In a systematic code, okay, we'll try to understand the systematic cyclic codes. Okay, and this would be the highlight of this session. Okay, so the systematic cyclic codes very similar to systematic linear block codes that we have studied in a couple of sessions earlier, where the first k digits, okay, the first k, in the sense the number of data digits that is fed to the encoder, the first k digits are data bits. So this is basically for the code word. Okay, then last n minus k, because we know that there are the code word has a length of n, then last n minus k, that's m digits, are redundant bits, or we can say them as parity check digits. Okay, so systematic codes are of course special case of general codes. Our discussion that we held in the last session applies to a general cyclic code. However, systematic cyclic codes are a special case, and we'll try to develop a method in generating systematic cyclic codes. Okay, before getting into any specific cases that you take at the end of this session, we'll try to understand in a mathematical way in general, then we'll try to understand for specific cases. Okay, so in general, I can say we have to note one of the important properties of cyclic code is that when we try to, based on, and I can say based on a property of cyclic codes, okay, which means the property is that if we try to multiply x power n minus k, where n minus k is equal to m, where it's number of parity check digits or redundant digits. So if you try to multiply this x, the highest order of this parity check digits, which is x power n minus k, times d of x, where d of x represents the data digits polynomial. When you try to divide this polynomial with the generator polynomial g of x, then we would get some quotient. We'll represent it as q of x, and some remainder at the end of the subtraction. We'll represent the remainder as rho of x, okay, where d of x is data polynomial, okay, g of x is generator polynomial. Okay, so with this division, the basic division rule, we can express the divisor. Okay, we can express this divisor, in fact we can express this dividend x power n minus k times d of x as divisor times the quotient plus the remainder. Okay, so all we have done is we have multiplied the data, incoming data polynomial with x power m, where m is the order of parity check bits. Okay, and we have tried dividing with respect to the generator polynomial. We have obtained some quotient and some random remainder. So with the basic division rule, we have expressed the dividend as the product of divisor and quotient and plus the remainder. So if I try to divide throughout, okay, throughout by the generator polynomial g of x, we get x power n minus k d of x gets divided by g of x, and here g of x gets cancelled, so this is q of x plus the remainder rho of x over g of x. Okay, and if I try to add rho of x by g of x on both the sides, or we can say if I try to move this the second term in on the right hand side on the left, so I would have minus rho of x by g of x, and we know that in case of a modulo 2 addition or subtraction, addition is similar to the subtraction performance, and the result of addition and subtraction are the same. So using modulo 2 subtraction, in other words it is addition itself. Okay, so using that I can take that the second term on my left, so this is x of n minus k d of x whole power whole divided by g of x. Okay, and if I take this second term on the left, this still I can call this as addition, okay, is equal to q of x. I can as well said that, so add rho of x g of x, rho of x by g of x on both the sides, and we know that addition of any two similar quantities in modulo 2 would result in 0. Okay, that would also have the same meaning, or would have got the same result. Okay, so this implies I can express this, the product of, I can express that on the right hand side is q of x times g of x being the common denominator, which is equal to x power n minus k, okay, times d of x plus rho of x. Okay, so we should observe a couple of points at this stage, where this will give us kind of an intuitive understanding of the nature of cyclic code. We know that d of x is of length k, in the sense the order of d of x is k minus 1. Okay, and we also know that g of x is of the order n minus k. We have seen in the generic case of non-systematic codes earlier as well. So g of x is a polynomial of order n minus k. Okay, and the product of x power n minus k being the power of x here, times the highest order, highest degree of d of x, which is k minus 1, the product of these two obviously will be at least or less than or equal to n minus 1. So therefore cumulatively the order of this product will be lesser than or equal to, I can say, n minus 1. N minus k plus k minus 1 would be n minus 1. So this implies that the left hand side should also, we know that rho of x would be definitely of a smaller order compared to n minus 1, being this as a remainder. Alright, so to match with the right hand side, on the left hand side as well, the order should be less than or equal to n minus 1. So this implies that, so this basic understanding of the product of the polynomials, this implies that q of x must have order less than or equal to what it should be. It should be, less than or equal to n minus 1 in total, so that this is already n minus k. Obviously this should be less than or equal to k minus 1. Okay, so this implies that with this a simple analysis, this implies that the product q of x times g of x, the q of x times g of x must have an order lesser than or equal to n minus 1. And we know that such polynomial which has order less than or equal to n minus 1, that means that this is one of the, okay, this is a code polynomial, because we know that code word length is n, and when we express in terms of polynomial, the order of a code polynomial would be n minus 1, and we can conclude that the product, or on the left hand side that we have here, should be a code word. So therefore we can express the left hand side as c of x as some code polynomial which can be expressed as x power n minus k d of x. Okay, this is how you would get the encoding part, where d of x would be supplied to you. Okay, with the knowledge of data polynomial or data vector, you should be able to encode it. Okay, so all we need to do is multiply this d of x by x power n minus k and divide the product by the generator polynomial g of x, and the remainder whatever that we get should be added to the product of these two. Okay, so that would give me the code polynomial for a given data polynomial. Okay, so of course we know that the first k digits in a systematic code word are precisely the data vectors themselves. Okay, that should be remembered. Okay, so of course this polynomial gives us the last n minus k digits, or in fact this will give us the product x power n minus k d of x. This implies that, this part implies that d of x is shifted left by n minus k digits. Correct? So x power I times some polynomial that we have seen earlier, that the polynomial itself will get shifted to the order of x by on the left side. I mean, if you shift d of x by n minus k digits, that is similar to multiplying with x power n minus k times d of x. So with this we can say, when d of x is shifted left by n minus k digits, we know that the length of d of x is the number of bits involved in d of x is k. So this implies that the first k digits on the left, correct? So since it is shifted left, the first k digits are exactly the data vector itself. Okay, and of course the remaining, whatever is remaining and last n minus k digits are parity check digits. Okay, so that's how we obtain a systematic cyclic code. Okay, of course this is cyclic code, but this is also a linear code that we have proved in the last session itself, but it was for non-systematic cyclic code, and this is the way to get a linear code which is cyclic and which is a systematic. Okay, so that's how we'll try to implement this for specific cases. Let's take an example at this point to understand it more better. Okay, all right. The example is about again 7,4 systematic. Let's try to construct a systematic cyclic code, okay, of n7 and k as 4, okay, using generator polynomial. Of course this should be known to us. Okay, using generator polynomial exactly with the one of the generator polynomials that we are taken in the last non-systematic cyclic codes was one of the polynomials that we took. I had said that there are two possible ways of using generator polynomial. Let's take the second one, which is x cubed plus x squared plus 1. Okay, and also consider, let us say, let's try to encode, since it's a 4-bit data digit, so obviously the data word or data vector is of 4 digits. Let us take one of them as say 1010. Okay, so this implies we have to express everything in a polynomial way, so that we apply the property of cyclic code. So this can be expressed as, so this is k bits, and hence the highest order would be x cubed, and x cubed does exist, then x square is 0, then is x. Okay, as I told, the first step in encoding this data vector is to multiply x power n minus k to this data vector. Okay, that's the first step. Okay, step 1. Okay, multiply x power n minus k with the data vector d of x. In our case, what would get? X power n minus k, n is 7 and k is 4, so n minus k would be 3, so x power 3 times d of x is x cubed plus x. This gives us x power 6 plus x power 4. Okay, and the second step is to divide this product. Okay, the second step here would be divide x power n minus k times d of x by the generator polynomial g of x. Okay, this is x power 6 plus 4, x power 6, x power 4. Okay, divide by the generator polynomial. The generator polynomial that you have considered is x cubed plus x squared plus 1. Okay, so it's a basic division of the polynomial, so that should not trouble us. So first term is x power 6, so and hence this is x power 3 to cancel out x power 6. Okay, so this would result in x power 6 plus x power 5. Okay, plus x cubed. So subtracting the result that would result in x power 5, which is the highest order. Okay, subtraction, as I told again, is similar to addition in binary. Okay, so x power 5 plus x power 4 plus x cube would be the resultant. Then next quotient is x squared, which is x power 5 plus x power 4 and x squared, and subtracting this would result in x cubed plus x squared. We can do one more division, okay, plus 1, that would result in x cubed plus x squared plus 1. So subtracting, the x terms gets cancelled, and finally we'll remain with just 1. Now the step 3, okay, the third step is to express or find out the code polynomial c of x, which is x power n minus k times d of x plus the remainder row of x. Okay, this would be code polynomial for a given data vector. Okay, so this implies for our case c of x would be the product that we have found out already, which is in fact x cubed times d of x, which is x cubed plus x plus the remainder is 1. So this would give us x power 6 plus x power 4 plus 1. Okay, so this is the code polynomial, and hence the code vector, okay, the code vector for 1 0 1 0 d of x for data vector, we would get this as 1, x power 6 is 1, x power 5 is 0, x power 4 does exist, x power 3 is not there, x squared is not there, x power 1 is not there, and we have x power 0, which is 1. Okay, and hence this is a 7-bit code word for a 7,4 systematic cyclic code. Okay, so this is for one given code polynomial. So if more data vectors are given to you, since it's a 4-bit data vector, as we know that there are 2 power k combinations of this data vector exist. So for 16 code words you have to perform in a similar way. So obviously, okay, so to obtain code word for all 2 power k data vectors, okay, this procedure would be cumbersome. Okay, so this becomes a tedious procedure. So what is the solution for it? I mean, how we can, although we have said that cyclic code is mathematically easy and to implement also, it's slightly lighter than the linear block code. So to make this easy, we have got a shortcut. Okay, the shortcut method is that it goes with the property of systematic codes themselves. Okay, we have seen that the first k digits in this case as well, the data vector was 1010, and hence the first 4 bits obviously should have been which parity check bits had to obtain using these 3 steps. Okay, so using that property of systematic cyclic code, we can use the shortcut method. The shortcut method is that by means of the code generating matrix. Okay, so this is by means of code generating matrix, which is G. Okay, by knowing by constructing G first, okay, we'll try to use the earlier procedure to compute the code words. Okay, so let's try to find out the code words for few specific data vectors. Okay, so a shortcut method is that find code vector for specific data vectors, the data vectors being the single ones, 1 0 0 0 0 1 0 0, okay, 00 1 0, and finally 000 1. Okay, so if we try to use the same procedure as earlier, we would obtain the code words as the following. Okay, so 1000 would give me obviously the code word as, okay, for 000, the first k digits would be 1000, followed by the parity check bits as 110, and for next data vector I would get this as 0100, followed by the parity check digits 0 1 1. So we have to find this using the similar procedure earlier, but we have to find out for only these 4 combinations of data vector. So there are only 4 here, so rest of 2 power k minus k would give me 16 minus 4, which is 12. For rest 12 data vectors, we would use the generator matrix, and we can use matrix multiplication to obtain the code vectors for rest of the combinations. So for the next data digits, we would obtain this as 0010 111. Okay, you have to put efforts for only these 4 data vectors. So this is 0001 followed by 101. Okay, so as I told, find C, of course, for this data vector using earlier procedure. Okay, the earlier procedure is using those specific flow of the steps. Okay, so once we have obtained this, we recognize that these 4 code words are the 4 rows of generator matrix, because that of having single one there. Okay, so next step here would be these 4 code vectors are the 4 rows of the generator matrix G. Okay, so making that, I mean, by constructing G, we have, therefore the matrix G is about these 4 rows. The rows are formed by these code vectors, so which is 1 0 0 0 1 1 0 as the first row, then 0 1 0 000 followed by 1 1, then this is 0 0 1 0 111, then this is 0 0 0 1 1 0 1. Okay, so that would construct the generator matrix. Then the next step is, of course, that we have done for even for the block codes. So find code words for other data vectors, I can say data vectors, using your simple matrix multiplication, where C was simply D times G. Okay, so this square braces implies these are the vectors, G is the matrix. Okay, just use this C is equal to D times G formula to construct the rest of the code in the table. Okay, so definitely this is an efficient method, because compared to the previous procedure, this is more efficient. Okay, this is efficient because of the fact that we will have to use, okay, we have used earlier procedure for only k data digits, correct, k data vectors, instead of instead of 2 power k combinations, we have used only for k data vectors, and for rest of 2 power k minus k we have used C is equal to D times G rule. Okay, so if you construct this code table for all other combinations, you can have an encoding table. Okay, and also we observe that for this case, if you construct the code table for this case, you would get the minimum Hamming distance between any two code words, that you would get as 3. Okay, you would get this as 3, as it is can be observed if possible in this first rows itself. There are 1, 2, 3, okay, 4. There are 4 Hamming distance between first 2 rows. Anyway, you can find out the minimum Hamming distance between any two code vectors once you construct the entire code table, and that would result in 3. And that we know that this is equal to the twice of the error correcting capability of this cyclic code, as 2t plus 1. So therefore t would result in just 1. So this is a single error correcting code. So single error correcting code. Alright, so next session we will try to construct generator polynomial. Here the generator polynomial was given to you, right? So in the next session we will try to construct generator polynomial for any cyclic code given. First we will see, as we did for this case and earlier case as well, first we will see the mathematical understanding of finding out generator polynomial and hence the generator matrix, and try to apply for specific case. It will also be followed by this is only the encoding part that we have discussed so far. The next session would also cover the decoding part, and hence one of the specific case as an example that would result in the complete generation of cyclic code and its error detecting and correcting capabilities for specific cases. Thank you.